So today we're going to talk about cans and cats, and so the specifically Kolmogorov Arnold Transformer, and this is a new type of transformer that would replace and compete with Transformers itself. I'm making this video because I've already tested this and it scores phenomenally in my test, which I'll show you, demonstrate, and then leave you to be able to conclude and run through these tests yourself. But so the bottom line is that this is an old method, right? The CAN method and this algorithm is older. It's an older algorithm, and then so essentially what they do is they just take this older algorithm, which has math problems when you try to turn it into a transformer. So a lot of this paper deals with the math. Here's like all of the math for the standard Kolmogorov Arnold network, and then so just a standard network, but then you can't scale it up, right? Because it runs into parameter computation inefficiency, like which is a common problem with scaling neural networks, right? And scaling matrices. And then so if you notice, if you look at this, not diving into a lot of the math here, but you'll notice this is all matrices, right? This is a matrix. This is a matrix array, what we're looking at here, and then here, and then here. These are all matrix arrays, right? And then so when you scale these guys, like when you put a bunch of these together, you generally run into computational problems. And then so a lot of the advancements that come about are in making this more efficient, making it more efficient to scale and put together lots of these guys, like this whole container, right? And then if you can do that more efficiently, it's the same way as like efficiently putting out and putting on more hardware onto silicon, right? Like it's the same type of concept, but with software. And then so going through their method is again, they just employ a bunch of calculus here, and then their method, and then they essentially are able to put this into a transformer. And then so here's the method, and here's their math for the transformer, and then here's all of the math and the final equation. And then so what this allows us to do is to create CAN-based transformers. And then so taking a step back from this, if you're not familiar with it, so all transformers are based off of perceptrons, right? And then perceptrons, like the bottom line is, perceptrons were created in the 1950s by a guy like me, and like someone far more into computer science than other realms of science, but has some understanding of like neurons and how they work, and then so takes this base process of neurons and then is like, okay, I think that here's my like, I'm not a neurologist, right? Like, but here's my simplified computer science version of what this would look like, and then if we put this into computer code, I would build out something called the perceptron, and then that's the start of all of this, right? And then so that's really it. It's not more complex than that. And then so we've been building on top of that ever since. And then so this CAN method, which came out about like 20 years ago, essentially is a different method than perceptron, right? Like, so rather than saying like, hey, neurons are perceptrons, and then like a simplified neuron would be a perceptron, it says, hey, like we think a simplified neuron would be more like a CAN. And then so that's what it is, right? And then so it incorporates different mechanisms within it than a perceptron would with regards towards the inner workings of it, but they both do the same thing, which is to emulate the inner workings of a neuron. And then so within this, essentially, I've created and tested out their methodology here, and then I utilized two methods here in my testing. And then so as I go through, and this research paper caught my eye initially, just going through a lot of these testing, right, and then looking at the math, and then looking over the math in general as I'm reading the paper, you start to say like, hey, like this is a puzzle piece that fits together with this puzzle piece, and like this would be cool with this, right? I think that this would actually work. And then so this, what I've done is there's a previous video that I've done on entropics, the entropics paper, and then entropics utilizes a method called entropy-based sampling. And then as I like look at the math of this CAN and like transformer, I realized I'm like, hey, this would couple really well with entry-based sampling, just in my mind. And then so I wanted to test it out. And then so this is a combination of the K&N transformer plus entry-based sampling. And then so within this, we can see it starts off with a loss of 1.15, and then goes down to 0.52, phenomenal. And then a test accuracy of 82.2%. Again, very good for this size of a model, right? The single layer, small neural network scoring 82% accuracy on the iris data set. Can't expect better than that, right? And then so just for comparison, here's a standard neural network, standard feed forward neural network. All of the standard mechanisms starts off at a 1.04, so it starts off actually a little bit lower, and then ends at a 0.81. So we can see that the loss rate throughout the training is not as good, and then it ends with a 71% accuracy, so far lower. Right, so then here's your testing, boom, everything that you need right here. Here's it all reproducible. It's just, I mean, absolutely smashing transformers and standard neural networks is basically, and perceptrons is what we're seeing and showcasing within this, right? And then so just showcasing another method here of another possibility of something that's going to be better than transformers. And then like to me, how I look at these things overall, I'll give you my very honest opinion of these things. Like I look at it, to me, it all boils down to, and I cracked it when I first started looking at swarm algorithms, right? And I look at swarm algorithms and these very simple algorithms, like these algorithms that are very, very tiny, they have intelligence inside of them. Like, and you can see that there's something that we would define as intelligence inside of these very tiny algorithms. And then, so to me, I couple that with a story which has stuck with me a lot, which is with regards towards slime mold, and it's scientific experiments around slime mold and how we've shown that you can scientifically show that same type of concept, right? That there's something that we would term as intelligence in slime mold, and that it's very efficient. And then so I think that like if you break down kind of like the core elements, right, and then like whatever once we get past the Higgs bosons and quarks, and we get like even lower than that, I think like whatever the base is like a algorithm for learning, like, and is in everything. Right, and then like this ability to learn to like what we classify as the building block of intelligence, I would say, is in everything. And then so within that, I essentially couple that with this overall, right, and then and with AI research. And then when I look at these things, I think that if that is true, then the framework would then follow that there's multiple paths towards quote unquote success, right? And then that there would be differing levels of success, and then different paths, and then some paths would be more quote unquote true than other paths, right? Like, and then so I think that the path that we're currently on is a path. It's a path that we have found that works because intelligence is in everything, right? But the path that we found is like a very brute force path. If you look at like the path and the progression that perceptrons have taken and what we've done, and then how we've gone from perceptrons and then modeling the brain and modeling the neuron to what we have now in a transformer, and then we've gone far, far away from the initial concept, right? And we've had to, because we've put in all these different things. Okay, this didn't work, let's throw this in. This didn't work, let's throw this in. And then we get to it and we get something that finally works, right? And then it's like, okay, now we're at the point where we have something that works. But what we're seeing now, and I'm thankful for it, with all of this research and funding and everything that comes in with all of the highlights and all of the like spotlight on AI, is more funding towards alternative methods like this, and we see that these alternative paths are more of the way. And then so I mean, very honestly, like I would say I bet like 80 to 90% that OpenAI is betting on the complete wrong horse. That's what I'm putting all of my eggs in this basket, honestly, like flat out right now. And that's the basket that I'm in, that transformers are not the way, and that brute force scaling up transformers might get us somewhere and might get us quote unquote there. But as soon as it does, and even if it does, it'll be surpassed immediately by some other method that is not transformers, and then that won't be proprietary to OpenAI, and that won't be proprietary to anyone, and then that's where we'll go from there. And I think that you'll find that it'll be like amalgamations is what you'll find, right? Like, so like chemists, like, I mean, the example that I can think of just off the top of my head as I'm thinking of this is like drug chemists, right? Like where they're able to if you outlaw one like classification of a drug, they're able to just classify and create through chemistry like a amalgamation of a very similar compound, right? AI operates that exact same way. Like it's exactly like that. Like if you like banned a certain portion, or you're like, okay, I am sending out this, then I can just create an amalgamation. Like, okay, you patent compound M, I can just create compound N, and it will do the same thing. And then there's nothing that you can do about it. And then also there'd be compound O and compound NN and compound N1, N2, and 3, like infinity compounds, right? And then you can do that and build that out in multiple ways. And that's to me how this technology is playing out as to how it works. And then so I think that again, if that's all true, we're like with transformers, we're in compound M, and then like compound M isn't that good. Like there's much better compounds than the compound that we're currently at. And then I think we're finding that out more and more. I'll link a link to this collab so you can test out my testing here as well as this paper, so you can go over and check out Kolmogorov Arnold Transformers for yourself. If you like this type of content, please like and subscribe. Thank you very much.